This time we're going to take a case where there is a given force, and we're going to vary the time interval to find out what happens to the change in momentum. This is different from the airbag example, where delta P was constant. That was the car slowing down from a certain velocity to a stop. Delta T was varied depending on the airbags and the safety belt, and the impact of the force on the passengers was found. So let's assume a baseball batter swings with a given force that is applied over the time interval of the ball being in contact with the bat. The ball will be approaching the batter with a positive momentum. We could have chosen negative, but in this case we'll choose positive. What is the goal of the batter? The batter wants first of all to hit the ball, and then his next job is to get the largest change in momentum possible for his force, and that force depends on his own strength and timing. The greater the change in momentum, the faster the ball will fly off his bat, which will result in it going further, hopefully to the seats. He's probably not thinking about getting a momentum change, but he does want to hit the ball very far. Now, of course, hitting a baseball is way more complex than the analysis that will follow. If you're interested in more information, please check out the book, The Physics of Baseball, which was written by Robert Adair, a Yale University physicist. What we have here is a given force by the batter, and the batter wants the largest possible momentum change. So there's the force. That stays the same. So what does the batter want to do? He wants to maximize the time that his bat, which is providing the force, is in contact with the ball. That means he should follow through with his swing. So by increasing the time that the ball is stuck to the bat, he'll increase the momentum. So the batter will be applying a very large impulse because he will have to reverse the ball's large momentum from the positive direction, heading towards the batter, thrown by the pitcher, to the negative direction, which is heading towards the center field bleachers. Now you can discuss or think about other examples. But again, make sure you decide which object in the collision is more affected by the force or the change in momentum. For example, with the car bags, you're much more worried about the people than the car. And which variables are capable of being varied. In that case, again, it was the time interval of a collision. So again, for the airbag, the car experiences the same impulse as the passenger during an accident. But a car is much less valuable than a human being. So it is more important for the passenger that less force is delivered to his or her body and more force is absorbed by the car. So here are the examples that we didn't talk about here that you can now think about, research, discuss, and that'll be quite interesting. The time interval delta t. The seatbelt increases the time interval that it takes the passenger to slow down. You don't go flying forward and hit the glass. The seatbelt has a little play, so you move a little bit, but then it slows you down when it tightens up. The biggest effect here is the airbag. That increases that time interval. It rapidly expands, providing a cushion that you strike. Then it deflates, and it's slowly compared to how fast the car has stopped, bringing you to a stop. Very analogous to if you fall from a height of 3 feet onto the floor, that hurts. Your time interval of this stop is very, very short. If you fell the same height onto a mattress, the mattress would give, increasing the time of you stopping. There'd be a greater time interval. Earlier we stated that delta P for this example, for the car airbag would be fixed, and delta T would be varied. Well, we just talked about why delta T is varied. Why is delta P fixed? Delta P is fixed because as long as the passenger remains in the car, which of course is another wonderful reason to wear your seatbelt, the car and the passenger started with a certain velocity and finished with a final velocity of 0 independent of the seats or the airbags. Whether you had them on or not, the car is going to stop. By rearranging the equation, F is delta P over delta T, where F represents the force delivered to the passenger due to the accident. We have the impulse momentum equation up here, where F delta T is equal to the change in momentum. And we did a little rearranging on the last page, and we had force is delta P over delta T. So delta P is fixed. So we just draw a little horizontal line there showing that it's fixed. Delta T, we've extended the time interval by using the seatbelt and the airbag. So delta T is going to increase. This is a handy little trick to see what happens to the various variables. If you increase the denominator, you decrease the entire number. So the force, and this is the force on the passenger, decreases markedly. That will mean less physical harm to the people inside the car. Another benefit from the airbag is pressure. Pressure is force per unit area. By increasing the area of the body that feels the force, remember the airbag is pretty big, less pressure is delivered to all parts of the body. That will reduce the chance of puncturing the body, which is also a very good thing.